Hello there, I'm going to work this two-dimensional projectile motion kinematics problem. It's kind of a spin-off from the homework problem that we have where you're considering a skier that's launched off of the top of a ski ramp at this angle of theta. V here representing the initial velocity, so I'm going to go ahead and give it the notation I like, which is V naught. And it lands at some time later on this ramp, which I'm just going to extend for the purposes of our discussion, that it lands down here. And you're supposed to calculate, if this is the position of landing, what is this distance of d? Well, what we're going to be looking at is what is the maximum distance d that can be achieved, and that's going to be in terms of this angle theta. What theta maximizes this distance d? But first we're going to kind of maximize the basic range equation. So consider first a projectile that begins and lands on a horizontal plane. So here's my horizontal plane. And the idea is I have a projectile, V naught, angle theta, and it goes up and it comes down and it lands on the plane. And this distance of r that you can find is well known as V naught squared sine of 2 theta divided by g. Now this is something that we've found together before when we worked the projectile motion problem. We use the idea that the final velocity vector, r sub final, was equal to r in the x hat plus 0 in the y hat. And we set that equal to our generalized force vector, which is v naught cosine theta time x hat minus g over 2 t squared plus v naught sine theta time in the y hat. And so this would equal to r and this would equal to 0, and we solved those to get this equation. So it's quite some time ago, but here's the equation. And the first part of the problem says, for this problem, which is just a projectile on the ground, landing on the ground, prove that the angle theta equals to 45 degrees gives the maximum range of a projectile. Well, we've actually graphed this before, and by graphing it, you can understand that if you plug in 45 degrees here, or pi over 4, that's going to give you sine of pi over 2, and it'll achieve a maximum at that pi over 4, and then it goes back to 0 again. Oops. Sine of 2 theta versus theta. Anyhow, we've already seen that that's the case, but let's prove it mathematically. And the way that we do that is by taking the first derivative of r with respect to theta and setting it equal to 0. So this reads, I'm either maxing or minning this r with respect to theta, meaning I'm really saying at what angle is this r maxed or minned, and in this case it is a max because a min would be the trivial case. And so I take a derivative of r, holding everything else constant. So v naught and g are constants, of course 2 is. And dr d theta equals to 0. Well, I'll pull out the v naught squared over g, and that will leave a d theta of sine of 2 theta. Derivative of sine, of course, is minus cosine, and here it'll be minus cosine of 2 theta times the derivative of what's inside, which is 2 theta, so the derivative of 2 theta is just 2. And I set that equal to 0. And all of these don't matter, they're just going to get divided out. And really what I'm looking at is cosine of 2 theta equals to 0. When does that happen? And that's going to be when 2 theta equals pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. But we're really only interested in looking at a smaller range of values that are associated with, this possible physical part. So maybe up to pi over 2. in this case. So theta can be seen to be pi over 4 or 45 degrees, and that's the angle that maximizes this. And one of the ways I know it again is if I do plug this angle in to here, this is going to make it sine of 2 theta will be 2 times pi over 4, which is pi over 2, and this will equal to 1, and that's the most that that can be, the sine function. So kind of following suit, we want to do the same thing, but for this distance of d. So first we're going to solve the problem, solving for d in terms of theta and phi, and then we're going to go ahead and take a derivative. So it's a little bit nasty mathematically, but it should be fine. I'll play around with it. If I get stuck, I guess I'll get stuck. But I'm going to have to use some trig identities and all of this. So let me get my sheet out here. Okay, so the first thing is, let me erase all of this. We'll just understand that we're going to be using this kind of basic idea that once I find this distance of d, so first I'm going to find d, and then I'm going to take a derivative. Ooh, I guess I should call it capital D. Let me do that again. I'm going to kind of find this distance. Let's call it capital D here. Just generally for any initial velocity, any angle. And then once I find d, what I'm going to do is to take a derivative of d with respect to theta and set it equal to 0. And then I'm going to solve for the theta for which this condition is met. So let's start by working the general kinematics problem and solve for d itself. So what I'm going to start by doing is I'm going to put my origin of the coordinate system up here. This tells me at time equals to 0 that I'm at 0 in the x and 0 in the y. So my initial position is really just the 0 vector. The initial velocity vector, as is standard for any projectile motion problem, looks like this. It has a v0 cosine theta component in the x plus a v0 sine theta component in the y direction, adding up to give the initial velocity. Of course, v0 and theta are constants in time. And then, of course, I understand that the acceleration due to gravity is just minus gy. I integrate that from 0 to t to get minus gty hat, and then I add in the initial velocity. Of course, that has an x and a y component, and so that's going to give me v equals minus gt plus v0 sine theta in the y plus v0 cosine theta in the x. Integrate one more time from 0 to t to get position, and then add in the initial velocity vector. Integrating this t will become 1/2 t squared. This is all a constant, integrates to t, and so I'm going to get minus g over 2 t squared plus v0 sine theta times time in the y plus v0 cos theta times time in the x plus my initial velocity, which I've already told you guys is 0. Right? That's what we talked about over here, because I put the coordinate system here. Well, after that, I have my function in time. I'm ready to solve the problem. I'm going to go ahead and take a look at my final velocity vector. Let's draw it. So here it is. If that's my final point, that's my final velocity vector. Let me kind of draw it officially down here. My r final. It has a magnitude of d, right? Just mimicking this. It has that magnitude of d. And this angle, of course, is phi right here. Now, this vector is comprised of two vectors, one in the x and one in the y, that I add together to make r final. And in particular, that's one in the minus y hat and one in the positive x hat. And if the hypotenuse here has a magnitude of d, This component here is the sine theta, or sorry, sine phi component in the minus y hat. And this one is the cosine phi component in the positive x hat direction. And those are my final position vector. So all I have to do is kind of write that out. Our final equals in the y minus d sine phi y hat plus d cosine phi x hat. Excuse me. And so what I'm doing at this point is I'm saying, well, this is my y function. At the final time, it's equal to this. This is my x function. At the final time, it's equal to that. And so I get these two equations, minus g over 2 t squared plus v naught sine theta times time equals minus d sine phi. I also get that d cos phi equals v naught cosine theta times time. And what I'm going to do is solve both of these for d really quickly, set them equal to each other, and then solve for the time. So solving for d, I'll get from here, d is equal to g over 2 t squared minus v naught sine theta times time divided by sine of phi. So I've brought this minus sign over and then divided by sine of phi. For my other equation, solving for d, I get v naught cosine theta times time. And so all I'm going to, divided by cosine of phi. So all I'm going to do is set them equal to each other and use that to solve for time. Excuse me, sorry guys. So setting them equal, d equals to d effectively gives me g over 2 t squared minus v naught sine of theta times time divided by a sine of phi equals v naught cosine theta times time cosine of phi. Dividing both sides by t, I get cancellation of one t, and I'm able to just isolate a single t and solve for that. So let me go ahead and bring this sine of phi over here. Then I'll add this term over here and just generally solving for time. V naught cosine theta, sine of phi over cosine of phi, brought the sine of phi over. Now I'm going to add plus v naught sine of theta. All of that's equal to g divided by 2 times t. And so I just have to multiply both sides by 2g. Over g, and I've solved for time. So at this point, what I'm going to do is I'm going to go ahead and plug that into one of my equations for d. Here's one. Copy that, put it on the next page. Let me copy my time. Put it over here. You put them together. D equals v naught cosine theta divided by cosine phi times time. V naught cosine theta, sine of phi over cosine of phi, plus v naught sine of theta, all of that times 2 divided by g. So now that I have d, what I'm going to do is I'm going to take a derivative of that with respect to theta and set it equal to 0. That means everything else I'm going to be treating as a constant here. So let me go ahead and highlight all my constants. My next step, I'll probably write this as tangent to phi. But right away, when I plug the d into this derivative operator, I'm going to go ahead and pull this out. So 2 v naught over g cosine of phi, derivative of respect to theta of this function. again, my constants, so I don't get confused. These got pulled out already. Then I'm going to take a derivative. Chain rule. First I'll take the derivative of this, leaving that constant. Then I'll leave that constant and take the derivative of this. So derivative of cosine theta minus sine of theta, leaving this constant. Then leaving the cos constant and taking a derivative of this. Oof. Didn't plan for room really well. Let me try to make a little. There we go. All right, so taking a derivative of this now, the cosine theta in the first term becomes minus sine theta. The derivative of sine is just cosine. And that's it. I'm setting that equal to 0. And I'm going to try to solve for theta now in terms of phi. This looks crazy, but it's okay because this is all a constant. And I'm going to go ahead and divide that out, and that's still going to leave 0 on this side. And then I'm just going to lose these brackets because this is gone. And what I'm going to do is I'm just going to bring this whole term over to this side, making it positive. So what that's going to look like is it's going to make an equal sign here for me and get rid of that. Now let's kind of multiply everything out. Excuse me. V naught sine theta cosine theta tangent of phi plus V naught sine squared theta equals minus V naught cosine of theta sine of theta tangent of phi plus V naught squared cosine squared of theta. You can see that there's a V naught in common in all of them. Oops. I don't know where that squared came from. That was a lie. Canceling that V naught out, I'm going to kind of regroup my terms here. So I'm going to bring this over here because they're like terms, right? And so I'll get minus 2 of those. And then I'm going to get, actually I'll bring this one over here and I'll bring that one over here so that I get cosine, cosine squared of theta minus sine squared of theta on this side, and then I'll get 2 sine theta cosine theta tangent of phi on this side. Now cosine squared theta minus sine squared theta can be written as cosine of 2 theta, trig identity, and 2 sine theta cosine theta can be written as sine of 2 theta. So what I'm going to go ahead and do is then just bring this over here and divide, and I'll get tangent of phi equals cotangent of 2 theta, which is cos divided by sine. Then I'm going to use the identity that tangent of phi is equal to cotangent of pi over 2 minus phi. And then I'm going to set cotangent of pi over 2 minus phi equal to cotangent of 2 theta. And then whatever is in the argument is equal. So what I get then is pi over 2 minus phi equals to 2 theta, or when theta equals pi over 4 minus phi over 2, and dang it, I am solving for theta. All right, that's it, good. So this distance d is maximized when theta is equal to 45 degrees minus phi over 2. That's exactly what this problem was asking for. Prove the maximum range of the ski jumper occurs for a launch angle of 45 minus phi over 2. I wrote it as pi over 4, but same thing. Prove this claim by deriving the equation above. Great. Does your answer make sense when phi equals to 0? Well, yes, because when phi equals to 0, I'm talking about that original problem. Right? So if here's my inclined plane, phi, when phi equals to 0, what's really happening is I'm kind of, making this into a horizontal plane, right? You can imagine this getting smaller and smaller as phi goes to 0 until eventually I'm actually just talking about the first problem that we talked about, which was if you call this distance d, we called it r, but if you called this distance d, that would effectively become our range. And you can see in the limit phi goes to 0, of course it makes sense because theta equals to 45 degrees, and I've recovered this kind of same problem on the horizontal plane. All right, so good times. Hope you enjoyed. Bye.